Hello, everyone. Welcome to our webinar. Thank you for joining us. We are very excited to be partnering with Nelson today to bring this information to you. The webinar today is Troubleshooting Multiwire Irrigation Systems, and we're just a couple minutes away from this awesome content. The webinar will be recorded and will be available on our website and sent out in an email following this presentation. It'll take about 3 to 5 business days to get it live online, but it will be available after the event. Also, we are going to allow all attendees to ask questions at any point throughout the presentation. So go ahead and raise your hand, use the chat box, and just let us know what questions you have. We're happy to answer those throughout the presentation. Today, the presenter is Alejandro Aste-Nieto. He is the Associate Product Manager of Irrigation here at Tempo Communications. A little bit about Alejandro. He strives to gather voice of customer insights for irrigation's electrical troubleshooting tools. Drawing from his experience in tech support, Alejandro possesses an understanding of irrigation system faults, tool tester functionality, and troubleshooting methodologies. He is committed to continuous learning, having attended various trainings from the experts in the field of irrigation and doing a lot of these trainings on his own. So today, Alejandro is going to take us through our presentation. Over to you, Hondo.
Let's get to it. We're going to be talking about electricity and circuits and how they relate to irrigation. We're going to be talking about multimeters, how to interpret them, and how to use those interpretations to troubleshoot irrigation systems and isolate problems to solenoids, wiring, or controllers. And then we're going to talk about the Station Master Pro, which also does much of what a multimeter can do for you and a little bit more. It can take some of these interpretations for you as far as what those measurements of a multimeter would be telling you, and kind of give you simple language. And it's got a couple other nifty features, including toning wires, so you can identify them out of a bunch. So without further ado, let's talk a little bit about electricity. It's tempting to really take a deep dive way too far into electricity, but just to go over the basics and kind of put some things in context. That in irrigation, we're only looking at a small number of kind of variables, but getting an understanding of how those variables work can help you get more creative in your problem solving. And some people might already know the majority of this stuff, but we want to make sure everybody's using the same terminology on the same page when they use multimeters to troubleshoot irrigation systems. So let's get into it a little bit here. So electricity at the most basic level comes down to positive and negative charges. So negative charges are from electrons, and positive charges are from protons. This is on the atomic level, and then sort of scales up from there. But these opposites in general are going to attract, and then similar charges are going to repel. So if you have an atom, an electron's going to want to sort of hang out with those protons in the middle there. And if you have a lot of electrons, they're going to want to spread out to other atoms, just to put it in the most basic terms. With conductive materials, the stuff that wiring is made out of, for instance, electrons are free to jump around from atom to atom. So electrons can move from one end of a wire to another, basically. The copper that they're made out of has this property where electrons are easy to jump from atom to atom, and they can be pushed with voltage to make that movement across a conductor. So in terms of what that means for us, we are going to look at the main variables in a circuit. So current, voltage, and resistance. We're mainly going to be looking at voltage and resistance. Current is going to be more important when it comes to locators, and especially with two-wire troubleshooting with a clamp meter. But voltage and resistance are what we're going to focus on today. So the lucky thing is, when it comes to these variables, they're pretty similar to how water will move through a circular system, loop. So that's the thing about circuits. They're always, or electricity always kind of moves in a circle. There's always a power source that the flow of current will leave and then return to. So here's our electrical circuit, and then here's our water flow equivalent over here. So when it comes to these circuits, when we talk about voltage, it's like water pressure. So here's our voltage source, right? It could be a battery, it could be some kind of adapter or something like that. But the equivalent in water will be a pump. So this is the motivational force pushing the material through the circuit. So in the image on the left, we're moving electrical charge. We're moving electricity in a circuit. In the image on the right, we're moving water through the circuit. And the motivating force there in electricity is voltage, and in water is water pressure. You can think of those as similar ideas. And then when it comes to the actual flow, you call it current in electricity. The symbol for that is I. You can think of that as intensity of the movement of the electricity. Whereas with water, we're talking about flow rate. So you would measure that in gallons per minute. Current we measure in amperes. That's the unit of measurement. Voltage you measure in volts. Current you measure in amperes. We call it amps for short. So the measure of current is the amperage. And then when it comes to resistance, it's like resistance in electricity is like flow restriction in a water hydraulic kind of a sense. So in the image on the left here, we have a light bulb, which is dragging on the electricity moving through the circuit and turning it into something useful in light. And then some heat is getting generated there as well. Heat loss, because heat isn't necessarily useful all the time. But on the right, the water wheel here, the turbine, is what's dragging on the system, introducing some flow restriction. And it's kind of the work that we're interested in doing based on the source of our movement in the pump. And you can also think of restriction in terms of the size of a pipe. The bigger of a water pipe you have, the more water will be able to flow through it with less resistance, right? Less restriction. Same thing happens in electricity with the gauge of wire. So a thinner wire, and it's going to introduce more drag on that electricity flowing through it. A thicker wire is going to be able to handle a lot more electricity flow without slowing it down. So in terms of how these are related, you can probably guess, but Ohm's law here puts it in a mathematical equation for us. Oh, excuse me, I skipped that. So Ohm's law here. So voltage divided by resistance equals current. And not only is that telling us, more pressure equals more flow, more current, and less restriction equals more current, more flow. But you can actually take the number of volts in a circuit from the power source, divide that by the number of ohms across the circuit, the amount of resistance in that circuit, and you will get the number of amps flowing in that circuit. Excuse me, I just skipped over something. Resistance is measured in ohms. It's called ohms, OHMS. It's signified by an omega symbol, which we will get to in a minute here. But you can take the number of volts divided by the number of ohms in the circuit and get the number of amps. The math will always work that way. So let's say we have 100 volts here. We have 20 ohms here. That means 100 divided by 20 equals 5 amps flowing through the circuit, the speed at which the electricity flows. So you can think of that in terms of, maybe 100 PSI here, and a certain amount of restriction here equals a certain amount of gallons per minute there. The math will work out in that simple way. V divided by R equals I. So let's talk about a couple of different kinds of current. There's alternating current and direct current. We are going to be mainly dealing with alternating current in this kind of irrigation system, multi-wire irrigation system. But just so you know kind of what the differences are, direct current is a constant amount of voltage pushing one direction, and everything is moving in a loop around in one direction. Alternating current, everything is getting pushed and pulled a certain frequency, and it's sort of vibrating the electricity going through a circuit. In the United States here, that's going to be happening at 60 times a second. Everything alternating current happens at 60 times a second here in the US. Other parts of the world, it's 50. Just one of those differences. But just to kind of talk about what is used where, AC is going to be on your high power lines outside, all the way into the plugs coming out of your wall, because it's just easier to move AC through longer distances with less loss. And the reason for that is because you can take a certain amount of AC and transform it to a different voltage without much energy being lost. In fact, when you plug in a controller, a lot of times it's taking 120 volts of AC and turning it into 24 volts going to your solenoids through the transformer inside the controller. So DC we tend to use in batteries and sensitive electronics, things like digital computers, phones, things like that. It's easier to convert AC to DC. It happens more often in that direction than the other direction. So typically things will start out as AC and end up as DC. We're not really touching DC too much in irrigation in the multi-wire system, like I said. But you want to know the difference because you have to measure them differently. If you measure volts, you have to know whether it's AC or DC volts, because a multimeter is going to be checking for completely different things here, right? Constant pressure versus oscillating, moving pressure. Same goes for current sometimes, although current is a little bit easier to sort of calculate one or the other. So for instance, our MM200 multimeter has a setting for AC volts, a setting for DC volts, and then it just sort of has current of either kind in different ranges. We'll talk about some of these symbols that'll help you interpret that. In fact, let's get to that right now. So here are the acronyms before we get to the symbols. Here are the acronyms in electricity that you'll want to know. AC, alternating current, that's the one that's kind of always vibrating back and forth in the circuit. DC, direct current, that's the one that's just kind of constantly pressuring one way. Anything battery powered, it's not doing anything at a frequency. It's just pushing in one direction. So anything battery powered is DC. Anything directly plugged into your wall and taking the power from that will be AC, unless it's converted somewhere along the way, like a laptop charger. So V for volts or voltage. Again, that's the kind of pressure motivating electricity. And if you want to measure that, it's going to be measured with a V next to it here, or you're going to want to select something with a V. The small m next to the V is millivolts. That means a very small amount of voltage. It's 1,000th of a volt. So it takes 1,000 millivolts to add up to a volt. So if you're measuring very sensitive small amounts of voltage, it's going to be more useful to you to think of it in terms of how many millivolts rather than how many fractions of a volt. A for amperes, we talked about that. That's the current measurement. Small m, large A for milliamperes. So again, same relationship. 1,000th of an amp is a milliampere. That's going to be important for the 2-wire troubleshooting with the clamp meter. It's usually pretty small amounts of current flow going through those circuits. This is the omega symbol that symbolizes ohms or resistance. That's what you're going to see on a multimeter here. So whenever you see that, you know that's the number of ohms, the amount of resistance. And I touched on it a little bit, but the higher the number there, the more restriction is happening. The lower the number there, the less restriction. In some cases, one is good. In some cases, the other is bad. We'll talk about all that. K, small k, means kilo or 1,000 times more. So whereas small m is 1,000th, small k is 1,000 of them. So if you have 1,000 ohms, that's 1 kilo ohm. And then mega ohms is 1,000,000, so even bigger, even more. Those, we're not going to get into kilovolts or killiamps or megavolts or anything like that. It's just with resistance. You will see high amounts of resistance and be able to interpret what that means for you. So EF, non-contact electric field detection. As far as multimeters are concerned, if they say EF, there's a mode that means you can hold up a multimeter to a power source and it'll start beeping without even needing to touch the leads there. So both our convenient little PM100 pocket multimeter and our MM200, our kind of more full-featured multimeter, have EF modes in them. So you might see those little non-contact voltage detector pens that you can hold up to a outlet and get it to beep. This has that feature in it. So we would just keep on clicking this single button until we get to EF. These laptops do a pretty good job of canceling any non-voice noises. So I don't know if you'll be able to hear it, but we got a beep coming out of the meter. Yeah, I'm not sure if you guys are going to pick that up in the mic. And then this one, you just turn this on and hold the EF button until it goes to EF there. And this can be held up to a power source and let you know if there's AC voltage nearby. We're going to talk a little bit about safety. You don't really want to trust those as much as you want to trust an actual voltage measurement to tell you if there's voltage. So hertz means the frequency, the number of times a second. Like I said, here in the United States, 60 times a second is the number of wiggles in our alternating current. So that's 60 hertz. So that's voltage pushing and pulling. Both of those things equals 1 cycle. So 60 push and pull per second is how fast our electricity vibrates here in the United States. Kilohertz, similar to kilo ohms, it's 1,000 times as many. So 1 kilohertz is 1,000 times a second. That's going to be more important for when we get into locators. And then OL, overload, that means more than a multimeter can detect. So if you're these are auto ranging multimeters, so it doesn't matter how little or how much of voltage or amperage or resistance it will take any measurement that it's able to take. So some multimeters you actually have to set, I'm looking for something between 0 and 20 volts, or 0 to 200 volts, or maybe sometimes with a resistance, 0 to 20, and then 0 to 200, and then 0 to 2,000, and all these kind of numbers. And you kind of have to take a guess at what you're looking for and set the multimeter appropriately. But this will actually tell you, oh, we're dealing with kiloohms. It'll put a K there next to the omega, or we're dealing with mega ohms. It'll put an M there and give you the number. So it'll range through these automatically. You don't have to set it. But that said, there's a certain threshold above which this is just not, going to be able to measure. If we're dealing with, over 600 volts, these multimeters are not going to be prepared for taking a measurement there. They will say OL, or, they might, they're not rated to be handling that kind of voltage. So if you see OL and you're measuring voltage or current, that's dangerous and or damaging. That's a lot. However, you'll see it very often with resistance, because if you're taking a resistance measurement and you're not touching anything, there's a virtually infinite amount of resistance happening between these 2 points. With enough voltage, you can get, an arc of electricity, but these multimeters are using very low amounts of voltage to test for resistance. So this is going to result in an OL reading on your multimeter. I'll turn the light on here so we can see a little bit easier. OL, nothing's touching. If I'm touching, 2 ends of a resistor, it'll give me the measurement of that resistor. If I'm touching these directly, it will give me 0. Sorry, it's hard to, there we go. Yeah, 0.000 ohms. There's nothing resisting between these 2 points. So you'll see OL until you actually touch something with these probes. Even after you touch something with these probes, maybe there's no continuity whatsoever on what you're touching. The 2 things that you're touching might not have any kind of connection. And we'll talk about what that means in an irrigation context in a minute. So on the multimeters themselves, they will put symbols to kind of symbolize these different ideas. So with AC, you won't see, if you're measuring AC voltage, you won't see VAC, you'll see wiggly line V, right? And that means AC voltage. If we see a straight line with a dotted or a dashed line underneath it, that means DC. So this is DC voltage that we're measuring right there. And then certain things they can measure both, whatever you throw at it. So this one, when you take current measurements, it can do either one, AC or DC. And that brings up a point. If AC and DC volts are kind of categorized so separately and are not interchangeable, then what does it mean to have one AC volt or one DC volt? Are they even the same thing? Well, what it means is the same amount of voltage on DC or AC through the same amount of resistance is going to give off the same amount of heat through that resistor. So, and again, resistance is not a property of either AC or DC. It's a property of whatever those currents are moving through. So it's like, our pipes. Those pipes are not, AC or DC pipes. They just restrict water by a certain amount. So if you have 1 amp of current, whether it's AC or DC, moving through a 100 ohm resistor, it's going to get hot at the same rate, whether it's AC or DC. And because the math works out to V over R equals I, as long as R is constant and either V or I are constant, it's going to be, you're going to know what the other variable is there. So now we get to the irrigation part here. So yeah, multi-wire systems turn on valves one at a time with 24 volts of AC going through a circuit. and then energizing a solenoid in the valve. So those circuits always consist of one zone station or valve wire coming from the controller to each and every valve out there. And then there's always a shared wire back from the valve to the controller that all the valves use as the return path. So as you can see here, we're engaging zone number 1 here, and it's using this, common wire, and then we're using valve number 2 here, and it's also engaging this common wire. There's voltage on this wire no matter which valve is on. There's current flowing through the wire no matter which valve is on. So if we put voltage onto 1 and common, we're turning on valve 1 over here. These other valves are going to be ignored because there's no voltage flowing through this as a circuit. What voltage is going to push from one end to the other. If there's high pressure here and low pressure there, that these other circuits are not affected. The movement of electricity is going to flow from the high pressure to the low pressure and not really take any detours. So you can use one wire to share between all the valves, and you can still turn them on one at a time. That's why it's called the common wire. And then some systems will have a master valve. So the master valve will control downstream flow to all the zone valves, and it will have to engage at the same time as the zone valves, or else those zone valves don't have any water to pass through them. These have their own little dedicated circuits that will be energized at the same time as these zone circuits. And these two will share the common wire. There's really no reason to add wires if you can just share the common wire for the master valve also. Some systems, they don't have a master valve. They're just constantly pressurized. Some systems, you'll actually have a pump instead of a master valve. Whatever water source, it might not be pressurized. It might just be a well or a lake or a pond, and you have to engage a pump to pressurize the rest of the system here. So in some cases, if it's not a pressurized water source, it'll be a pump. For a pressurized water source, it'll be a master valve. Then I mentioned the word solenoid earlier. That's the portion of the valve that gets energized and allows water to flow through the valve. We're not going to get too much into how that happens, but as far as electricity concerns, this is where things end, and then things become hydraulic. So we have these nice little diagrams to kind of show us, how these circuits work. But in reality, we have to picture where these wires are going in the real world, and what might be going on between them, or between the controller and each valve. So, in reality, things can get a little bit more complicated. Over here, there's one valve, and then the rest of them are over here, and there's a wire going to each one, and then one wire linking all these valves on the way back as the common wire. So let's say we have, this zone right here, it'll have the yellow wire going out there, and then a common wire on the way back. Usually that common wire is going to be white. But that common wire has to meet up with this valve here, and this valve will be using the common wire as well. So even all these little sections between the valves that have a white wire, we consider that the common wire, even though it's not one continuous piece of wire. It has to splice in with all these valves. So, as you can see here, this is the only part of the wire that is shared by all the valves. This is only shared by 3 out of the 4. We still consider that common wire because it's shared. And here's some more kind of logic behind the configurations you might see. If you have a valve manifold, your common wire might be extended all the way out to that manifold and be shared right away by all of them. Whereas there isn't really common wire daisy chaining linking between the valves. Whereas here we have common wire going to this valve and then to this valve and then to this valve and then branching off to this valve, but also to this valve and then this valve. So here's a section of common wire. Here's another section of common wire. Here's another section, different valve, and then we have this whole other branch over here. And these two, you might even call 3 branches of common wire, all have to kind of meet up and consolidate as they go back to the controller. So they might all get spliced together here, and this is just one piece of common wire. Somebody might have 2 pieces of wire here, and they're both just sort of connected to the same port here on the controller. Some controllers have more than one common wire port, and that might be done because you have kind of one manifold on one side of the building, one on the other, and you want to be able to troubleshoot them separately and kind of simplify your troubleshooting process. So we have to keep that in mind when we're troubleshooting and kind of picture how things might be laid out there. And that said, if all your valves are having issues, that could just be something wrong with the controller or something wrong inside the controller. If everything else in the system is good, but your controller is bad, nothing's going to work. Meanwhile, if you have a problem in the common wire after it's being shared by all the valves, nothing's going to work there either. These valves are not going to have a circuit completed. They're not going to, no matter how the controller tries, it's not going to be able to engage any of these valves here. And it could be the master valve. If the master valve is not opening, these are not getting pressure. The solenoids could be working properly, but there's no water pushing to allow through the valve. And there has to be water pressure to even engage the mechanical diaphragm in the valve out of the way of flow. So could be any of these things. If nothing on your system's working, those are the places to look. We'll treat them accordingly. And then if you have an issue with one of your valves or multiple valves, but not all of them, you can eliminate those previous possibilities. If you have one of these valves working, your common wire out here can't be broken, because then it wouldn't have a return path. Same with the master valve. If the master valve is not working or not opening, I should say, then you can't have any of these downstream valves get pressure and they won't work. If your controller's busted, there's no way any of these valves are going to be working. So it could be just one of the ports on the controller, one of the terminals here isn't getting voltage or not getting enough voltage. Could be one of the zone wires is damaged. Could be one of the solenoids is bad. I don't think I listed it, but it could be the splice from this wire to the solenoid. There's a bad splice in there. So one more possibility is that the link between a couple of valves could be defective, taking these ones out of operation. And we can use multimeters to help us diagnose any of this stuff. We can check the controller, we can check the zone circuit, and then break that down into whether the problem's in the wiring or in the solenoid. So let's talk about all that. So resistance is how we're going to check the zone circuit, the wiring and the solenoid. Before we check resistance, you always want to do voltage first. Don't check resistance without voltage for a few reasons. For one thing, it's just good practice in terms of safety. You wanna make sure that there's nothing that can hurt you before you touch it. So and to be extra safe, wear gloves, especially if you're dealing with higher than 24 volts of AC. Another safety mechanism, another piece of good practice when it comes to checking voltage is to only use one hand when you're holding two probes. The reason for that, if you're using both hands and you somehow make electrical contact with your hands, there's going to be a circuit completed from this hand to this hand, and it has to take a path up your arm and then down your other arm. And that goes right through your chest, and your heart is an electrical organ, so that is especially dangerous. If you use one hand, the worst case scenario is electricity takes a path through your fingertip, and that hurts really bad. But that is much better in comparison. The other reason you want to check voltage before you check resistance is when you're checking resistance with a multimeter, it is not expecting voltage. So even 24 volts of AC, if you leave a meter on a resistance reading mode hooked up to that kind of voltage long enough, it's going to be heating things up that are not designed for that kind of voltage or that kind of heat. That said, one great thing about our pocket multimeter, our PM100, is it starts up in auto mode, which take resistance readings by default. So here I'm just getting 0 ohms, obviously. However, if you go and you touch something with voltage, it's not going to take resistance readings. It's going to tell you the amount of voltage. So it does that work for you. Not only that, but it will tell you whether that is AC voltage or DC voltage and tell you the appropriate amount of voltage. The battery here, and we're going to see 9.63 volts there. I don't know if I have any AC plugs within reach. Let me see. One hand on that. Not sure how well that'll show up, but that's 119.8 volts, 120. So it'll do DC or AC voltage, or if there's no voltage, it'll tell you the resistance. It'll tell you the ohms. Pretty nice little feature there on the PM100. So the other reason you want to check for voltage first is even if there's a little bit of voltage, it could affect your resistance readings because these are using small amounts of voltage coming out from one of these probes, putting positive here and negative here and trying to push a little bit of current through whatever these are touching. It's going to measure that amount of current because of the Ohm's law, I equals V over R. And from the amount of current that is flowing through the circuit created by these probes, it will be able to calculate with precision what that resistance is. So if you have some other kind of voltage here introduced in the circuit, it's going to affect your readings. It's going to give you something incorrect. So always check for voltage before resistance is the lesson there. So now that we're testing voltage, we can test the input voltage into the controller to make sure that that's not our problem. And here in the US, things used to be, I think, 110 volts, and then they got raised to 120, but things can kind of be sort of in that range, 115, 120. Your transformer in your controller should be between 24 and 30 volts of AC. Let's see if I can. Here's our terminals here. Not sure how well that shows up. There's a couple terminals inside that say 24 VAC. Those are directly coming out of the transformer. So you can check that. If you're not getting at least 24 volts, replacing that transformer, which is a replacement part, most of the time anyway, replacing that transformer will likely take care of that, take care of whatever issue your controller was having. Individual station and make sure you're getting 24 volts. Sometimes one of them will be flaky and it won't be a steady 24. It'll be kind of jumping all over the place. And that is not going to be good enough for valve solenoid out there. So in terms of testing resistance for our zone circuits, if you get a low amount of resistance, that means something is shorted. And a little bit here. So in that image there, you see we have one probe touching the common terminal. So there's a screw attached to the common wire. And we have one screw on our zone circuit. We can just touch, as long as there's no voltage, we can just touch our probes in the controller to the, we can touch our probes to the terminals for the common and whichever zone circuit you are checking while the multimeter is in resistance reading mode. And it will tell you the amount of resistance in the zone circuit out in the field, in the wires going out to the solenoid. So out one wire through the solenoid and back. So yeah, disconnecting these wires from the controller is not necessary. Never is a bad idea to disconnect the wiring. You never know what's going on in the controller. It might be throwing off readings, but typically you don't need to take that step. But what a low amount of resistance is saying is that either you have wires touching out there in a way that they shouldn't be in terms of common and zone, or your solenoid is burned and failed in such a way that it is fusing a couple of things together that shouldn't be touching, and it's bypassing the coil inside of the solenoid. So that could be a wiring problem, or it could be a solenoid problem. But what it's saying is the solenoid itself is being bypassed. So one way that could happen is if there's moisture in a valve box and you have two bad splices on that solenoid, and the water is creating a short circuit across those two wires. Electricity has an easier time through the wet dirt or the water in there than it does through the solenoid, and it's creating a short. And then what we're looking for is between 20 to 60 ohms for these zone circuits. Solenoids are going to typically be between 20 and 60 ohms of resistance themselves. The wiring going to the solenoids are hardly introducing any resistance. So think of our water wheel. You know, the tubing carrying the water is going to drag on the water a little bit, but nothing compared to that water wheel, right? So let me see. Here's kind of a generic hardware store solenoid. We can check the resistance on it. Let me light up the screen here so it'll be easier to see. And getting 25. I can show that to you guys, I think. Give me a second. But yeah, you're looking for the 20 to 60 ohm range. It's about 24 and a half. Hunter solenoids are going to be typically about 25. Rainbird are going to typically be about 35, and they're going to kind of be stick to a more narrow range from manufacturer and model. So, if you see a Hunter solenoid, it's giving you 60 ohms. It's still in that range, but it's a sign that that's a failing solenoid. So if you're doing preventative maintenance, you might want to get to know your system a little bit better, check the specs on each manufacturer of solenoid, and kind of narrow down your range to whatever that spec is. 20 to 60 is kind of a catch-all because some manufacturers you might see 20 consistently, some you might see 60 consistently. I think like Orbit is 60. But you know, there's going to be some exceptions. Some are less than 20, some are more than 60. But for the most part, 20 to 60 catches a lot of solenoids when they're good. If you see above 180, you've definitely got a problem that's going to be affecting that valve. If you have above 60, but not too far above 60, you might still get some intermittent operation depending on a few factors. But above 180, you've definitely got a failure. You've got a valve that won't open. That could either be because the splice is bad, could be something in the wiring. The is broken or it's nicked and there's corrosion. Could be that the solenoid has failed open. So when solenoids fail, I just had one more to go. So when solenoids fail, it's usually because of heat over time and things kind of melting, and they might either melt together when they shouldn't, or they might melt and apart. So bad solenoid. You might also see numbers jumping around when you're taking readings. You might see things kind of moving in a weird way. You want to see a constant number between 20 and 60. But if you see something much higher, that means there's a break somewhere. Somewhere in that circuit, there's a break. Or there's corrosion adding resistance. So one little caveat here is if you have 10 to 20 ohms, you might have two valves hooked up to the same circuit. And that's not typically a problem electronically. Most transformers end up just having to put out more current, and they might get a little bit hotter, but they should be able to handle that extra current. Usually the bottleneck in more than one valve is water pressure. You might not have enough water flow or water pressure to be opening two valves at once, but that's kind of one of those things that you'll have to kind of case by case. So 10 to 20, that's an indication of perhaps two valves in the same circuit. So kind of picturing what we're talking about here, the resistance on this wire out to the solenoid is pretty negligible. Depending on the gauge of wire, it'll introduce, smaller wires will introduce more resistance over their length. Like we were talking about, smaller tubes are going to drag on water and restrict that flow. Same goes with wires, but even 18 gauge wires, it might be, I think, like 8 to 10 ohms of resistance over 1,000 feet. I forget the numbers, I'll have to check, but 12 gauge wire, it's like 2 ohms over 1,000 feet. It's going to be small in comparison to the amount of resistance that the solenoid is introducing into the circuit. So if you have voltage here on station 4 between common and terminal 4, it's going to be pushing current through the wire without much resistance, and then the solenoid is going to be adding that the bulk of that resistance, and then we're back to free flowing through good wire all the way back to our terminal here. So longer runs of wire, they'll increase the resistance by a little bit. Smaller gauge wires, they'll increase the resistance by a little bit. Smaller gauge wires, there's going to be a maximum distance that you can have a valve from the controller. So if all the zones are high resistance or OL. Like we said earlier, that's an indication of a break in your common in there. However, if you have consecutive valves that are out, but not all of them, you should probably suspect that it's the common wire after those two failed valves linking to the good ones. One thing you can check is you can take a resistance reading. Instead of between common and one of these numbers, you take it between two valves that are out, and you can check and see if everything from their valve wires all the way to their solenoids, all the way to their common wire linking them is all good. This will do is it will show you the amount of resistance introduced from this wire, which again is not going to be much, the amount of resistance introduced by this solenoid, which is going to be 20 to 60, depending on the manufacturer, the amount of resistance from this solenoid added to it. So we're basically doubling the amount of resistance from one solenoid, and then again, kind of negligible resistance here back on this wire. So you might see 50 ohms between these two zones, 3 and 4, if you have two 25 ohm solenoids, like their Hunter solenoids. So 50 ohms between these two wires, because the only path that can be taken here is through both solenoids. Now, they might not be working, but that doesn't introduce any problems in this path here, right? So taking a measurement here and seeing 50 ohms indicates, it confirms that there's nothing wrong with this section of our circuit. So we can narrow things down further to this being our problem area. If we have a manifold and we're not getting continuity on this wire to the common, it could either be the wiring going to the solenoid, or it could be the splice here, or it could be the solenoid here, or it could be the splice here. In theory, it could be this section of wire here, but it's a pretty narrow number of possibilities that it could be. We can narrow it down a little bit further to either solenoid or wiring pretty quickly. You can test the resistance in the valve box. You can actually turn on the zone for that valve box and go to the valve box and check for anything obvious, if it's bad splices or a lack of voltage there in the valve box. Again, you'll want to check kind of 19 to 28 volts there in the valve box, accounting for some of that resistance from the wiring. And if you have significantly less, then that indicates a wiring issue. And then from there, we can check our solenoid very easily. Check the two solenoid wires like I did earlier with those two probes, and look for that 20 to 60 ohm range. And if you have that 20 to 60, that solenoid is fine. It's not the problem. If you see less than 20 or more than 60, that's a bad solenoid. Like I said, if it's jumping around, that's another indication. We can further confirm if an issue is in the wiring. So what we can do is short the zone in common wires there in the valve box, and we're taking the solenoid out of the equation. We go back to the controller, measure the resistance between those two things, and it should be less than 10 ohms. Only the resistance of the wiring itself, which isn't very much, like we said. Furthermore, you can check and see if there's any nick in your insulation on your wiring, which could be introducing corrosion. You can check the resistance from these wires, between these wires and the ground itself. There's a couple ways you can do that. You can either take one of these probes, touch the circuit wiring, and then take the other probe and literally stick that into the dirt underneath you. Or better yet, you have a screwdriver, stick that into the ground and touch this to the metal of the screwdriver. That's going to be making a better contact. Or that controller might be hooked up to some kind of ground, either through the ground lug in the plug or by splicing that in on the green wire in there. So you can touch whatever the green wire is hooked up to, and one of your wires. And if there's anything other than high resistance, high resistance, or OL, then there's compromised insulation in a wire somewhere, or a compromised splice in a pull box somewhere along the way, something like that. You should see like OL, maybe mega ohms. Otherwise, kilo ohms, you might not have a problem now, but that means you're introducing corrosion because there's insulation that is compromised. If you have resistance a lot lower in the hundreds or even less than 100, you've got a big time fault in that wiring. So if you see infinite resistance between that wire and the ground, you can eliminate that as a possibility. So if your controller is good, if your solenoid is good, if your wiring is good, you've got something outside of electricity that is causing a problem. It could be something in one of these valves hydraulically, anywhere from a bad diaphragm to a clogged hole underneath the solenoid, preventing it from doing its job. There's this little port in here. Sometimes pieces of glue from PVC will get clogged up in that solenoid port, preventing this from doing its job. Could be a ball valve is not turned on somewhere. Could be your master valve is not working. Could be a rain sensor out there that is unhooking the system. Some of the old school rain sensors that weren't hooked into the controller, the way they worked is they would get spliced into the common wire, and then when there's rain, they would disconnect the common wire, and the controller would try to work normally, and the rain sensor would deactivate that circuit by breaking the common wire on purpose. And then when it dries up, it'll reattach. So something like that could be your issue. So 24BK, this is going to do a lot of what we just talked about in terms of narrowing down issues and troubleshooting, and a little bit more. We can activate solenoids, battery-powered AC voltage source right here in your pocket. We can either turn them on continuously for hours, or we can chatter them, which will help us locate hidden valves by ear. They will tick on and off a couple times a second, and you can go out into the field and listen for this clicking to find a valve. Let me do a demonstration. Not sure how well the filtering in this laptop is going to prevent the sound here, but an audible click. And one thing I'll say about that is some manufacturers of solenoids will be louder than others. Typically, Rainbird is very muffled and pretty much impossible to hear. However, Hunter and Toro are pretty loud. Furthermore, if you empty the water from the valve, it will echo the sound a lot better. So if you have a way to depressurize the system in the valve that you're looking for, it'll only help your sound when you're doing a chatter. We can test zones and solenoids for continuity, and instead of checking for number ranges, it has these LEDs that will tell you exactly what's going on. And we can also send a tone onto a wire so we can tell how to find that same wire on the other end after it's been buried in the ground. Furthermore, you can test the controller for a good 24 volts of output, the transformer or the station output. So this will activate even surge protection solenoids such as Toro Spike Guard. This thing right here has a capacitor in it, which will prevent you from seeing a good reading on a multimeter. It'll just say OL. There's no, a capacitor isn't making a full metal to metal connection. However, AC can go through a capacitor. So this will test that correctly. I will demonstrate this right now. Here it says good. We got a green light. All good. However, our competitor uses a similar, makes a similar tester, but they use DC. This is a DC voltage source here, and that is not compatible with these surge protected solenoids. So nifty feature on the 24B that is unique, that as far as I know, there's no other tester on the market that can properly test these surge protected solenoids, including multimeters. So we can do all this from the controller. We can do this in the valve box. And as I mentioned before, we can chatter valves to listen for them. Ideally, you'll have a locator, but this will get you through in a pinch. And when it comes to the continuity test, you're going to want to disconnect from the controller in this case because there's voltage being sent. And rather than check for 20 to 60, this is going to do all the math for you and just light up green. Or it'll light up red when there's a short, or light up red on the open indicator when that is the case. This will also, if you get the kit with the little probe, it'll put a tone on the wires so that you can identify them. So what that means, what that looks like, if you have a pull box with a whole bunch of wires in it like this, you might not know which wire to look for here. But this will make a sound louder on the one that you're hooked up to with the 24B on the other end. You can either do this going from controller to valve box or other way around, from valve box to controller. Both are pretty handy. So what this looks like, if you're toning from controller to valve, you'll stick one of these clips onto your valve wire. The other one, you will be able to either clip it to the ground of an outlet in a pinch if you're in a basement or a garage. But better yet, you might as well just clip it to the common wire. What that means is you'll have tone on both wires, common and valve. But hopefully your common wire will be a different color and you'll know one from the other. But best case scenario, you can actually clip the second one to a ground stake in the dirt or screwdriver in the dirt. That's actually going to give you the best tone on the valve wire, give it the loudest response. Because the wire is buried in the dirt, it's got a capacitive effect there. And then other way around, you're in a valve box, you'll have easy access to the dirt. You can just use a ground stake or a screwdriver every time. Identify what number that valve corresponds to in the controller. Easy peasy. Then when it comes to the output test, you can put this in the off position, and if it's hooked up to 24 volts of AC, it'll light up this little green LED here. Do I have 24 volts really available? Let's see. There we go. Got a green light here if you guys can see it. Hooked up to 24 volts AC. You want to see that as a steady, solid light. Otherwise, there's an intermittent, fluctuating voltage issue. which will not work for your valves. So again, we are eliminating possibilities. If your solenoid is good, if your controller is good, if your wiring is good, somewhere else, master valve, ball valve, hydraulic problem, diaphragm, rain sensor. So these are very useful tools to help you figure out how to narrow down problems, what they're going to look like. It'll help you understand what to do next, or if you really want to save time, it'll help you figure out what locator to use. You might know that the problem is somewhere between controller and valve box in a wire, and a locator is going to be very helpful in narrowing down where that problem is located. So just to summarize, when it comes to electricity and circuits, I equals V over R is what we call Ohm's law. It's the relationship between current, voltage, and resistance. I stands for current. You can think of it as intensity, but it's measured in amps, which is A for short. And then V equals voltage, which is measured in volts. R in that equation is resistance, which we measure in ohms. That's the omega symbol. Think of current like water flow. Think of voltage like water pressure. Think of resistance like flow restriction. When it comes to multimeters, you can narrow things down from controller with the voltage. You can check the voltage at the valve box. If you have low voltage there, it's a wiring problem. You can verify this with resistance. 180 or higher is an indication of a wire problem. A few different flavors. If you test a solenoid below 10, it's shorted. That should say 20 to 60 is good. Above 180 to OL or infinity or whatever, you got a bad solenoid for sure. You have fluctuating numbers, you have a bad solenoid. Station Master Pro makes it easy. Red equals bad, green equals good. Red will kind of tell you what kind of problem. And then it's got that 24-volt indicator. It's got chatter mode and can send tone on wires, so you can identify wires from a bundle. One thing I forgot to mention is that there's LED light on here that will light up at a certain amount of signal detected. Again, not sure how much of this you'll be able to hear through the mic to me, but these mics filter things out. So this will light up when there's a certain amount of signal detected. You can do is dial in this sensitivity knob so that only touching one of these wires will make it light up. Can't really demonstrate it without a live system here, but you can make it sensitive so that only one of these wires with carrying your tone is going to give you a visual indication. So this is the portion of the webinar where when we were live, I was asking for questions. But like I said, we had to kind of re-record to get the full use out of all these slides. If you do have any questions, please email me. My email is Alejandro, ALEJANDRO .ASTE, ASTE -Nieto, NIETO @tempocom.com, TEMPOCOM.com. I would love to hear from you. I love talking to customers. I learn something every time I hear somebody come with a question. So would love to hear from anybody out there who wants to talk about troubleshooting multi-wire systems. Next up, we have our locator webinar. Maybe by the time this is reposted, that will already have passed. But soon after that, in 2 weeks, will be our 2-wire troubleshooting seminar. So hope to see some of you guys joining those webinars. And like I said, reach out to me via email anytime there's any questions about any of our irrigation products. Would love to hear from you. Thank you so much, and happy hunting out there for your troubleshooting issues. Thank you.
So with that, just want to throw it out if anybody has any questions. I know we're kind of new in the Australia market, so if anybody, you know, is wondering anything about any of our products, doesn't have to be any of the ones that we went over today, but you know, feel free to throw anything out there. We'd love to hear from you. We appreciate that we're connecting with you for the first time. So please ask away. Right. So yeah, there's a lot of fans of Station Master out there. That's, I mean, in terms of quantity, that's our #1 seller in irrigation. You know, it's very affordable for what it does in terms of troubleshooting. It's very handy. It fits in your pocket. So yeah, very portable and super useful in a lot of troubleshooting ways. You know, our locators are also very popular, but Station Master is #1. Yeah, multimeters are very powerful if you understand the theory and practice with them in narrowing things down. And it's just fun to kind of get an understanding of what's going on out there in your system.
And yeah, yes, Nelson all these products. Yeah, go ahead.
Yeah, is our partner out there in Australia that offers any of these items and more. We'll be talking about more of them down the road. Yeah, thanks to everybody with Nelson for everything you guys have done. It's been great working with you guys so far, and seems like it's been positive feedback for everybody out there in Australia as far as using the Tempo products. So, been good.
All right, Alejandro, I think we're done for today. Thank you everyone for attending, and we look forward to seeing you in a couple weeks at the next webinar, which is locating irrigation systems, wires, valves, and faults. So don't miss that one, and we'll send this out also as a recording. So thank you. Have a great day, evening.
Thanks, everybody.
Bye.